So, good afternoon. We are here in the auditorium of the Pavilion of Knowledge, but in fact, we are in a much larger garden. Here it's this garden in Lisbon, and we know there are many gardens all across Europe in the Ars Electronica Festival. Today we have here with us Professor Rui Agostinho from the University of Lisbon. And as you have just seen, he was the scientist who was invited to explain how do we measure, how do we know what are stars made of in the clip of video that you have just seen. So now you will have the opportunity to ask him questions. So hello, Rui.
Hey, hello. It's very nice to be here. It's always a big pleasure to talk with people about this stuff.
I know you love this. So, right now we had some questions in the live stream that were presented. We have here the questions from two young girls, Inês and Sofia. They are 13 years old, and they ask, how many stars can we observe from the Earth? So this is one of their questions.
That's a very nice question, and when I read that question, I was thinking to myself, okay, what do exactly they want to know? Is it the number of stars we observe with the naked eye, or just in general with our telescopes? Because you can think on these two levels, and with the naked eye, of course, there is a small number of stars that we can observe. And the reason for that is the size of our lens in the eye, the pupil, is very small. So the eye, when it is night, when we don't have the lights of the sun or light bulbs showing, our pupil opens up to about 7 millimeters. So it's a very small telescope. The gathering power is very small. So basically when we look and we are not inside the brightness of a big city, if you go into the fields with a dark sky, we can see not really that many stars in the sky. In the northern hemisphere, we see less stars that we see in the southern hemisphere. The reason for that is, if you look at the galaxy, the axis of rotation of the Earth is tilted in a way that the northern hemisphere is looking towards the outside of the galaxy, where there are less stars in the sky. If you live in the southern sky, the southern part of the globe, then you see the center of our galaxy really up in the sky. So we can see many more stars. If you sum up all of that with the naked eye, it's roughly about 2,500 stars.
2,500?
2,500 is not really that much. But if you put on some telescopes, now the size of the gathering power, the size of the lens increases. If you go to binoculars, you go to 25 millimeters, 50 millimeters. If you go to telescopes, you are talking about meters of gathering power. And suddenly we are observing the total number of stars in the galaxy. Almost. We don't see all of them. We don't see.
But even so, that is if we are lucky to have a place with a dark sky, because otherwise you have the terrible problem of the light pollution. So you could even see less.
Oh, much less. In a big city, you see just a few hundred stars.
There is another question that is a bit related to that, is the total number of stars in the universe. Has anyone calculated? Note that this is a question made by two young girls, so it's really...
Yeah. That's why I gave the first answer sort of linking already to this second one. Yeah, that's a very good one. And of course we do calculate them. I was saying that even the telescopes cannot see all the stars we have in the sky. And the reason for that is, besides stars in our galaxy, we also have dust. and dust really hides the light from the very faint stars on the other side of the galaxy. So we cannot count them one by one. That's some sort of impossible. But we can actually calculate how many stars the galaxy has. Yes, that is possible to do. And one thing is, and I'm already connecting to one of the other questions we have here, is to do something like this. Okay, what is the weight of the galaxy? How many kilograms the galaxy has? And the answer is very simple. You put the galaxy into a scale in the bathroom, put the galaxy over there, and see how many kilograms.
And how would you do that?
Oh yeah, okay. Let's start with something smaller. We start putting the sun. There is another question about the mass of the sun. We put the sun on the scale in the bathroom and see how much it weighs. How do you do that? The scale is not exactly the scale in the bathroom. We do that using the laws of physics. Basically, for the sun, it's very easy. We know that the Earth goes around the sun in 365 days. And we know the distance between the Earth and the sun. If the Earth is going around the sun with this velocity, then the force of the sun on the Earth must be, and can be calculated, as some number. And that force is produced by the mass of the sun. That's how we get the mass of the sun.
That's your scale.
Yeah, that's my scale.
You
So the answer to this question is the mass of the sun is very big. It's 10 to the 30 power, to the 30th power. 10 to the 30 is a huge number. It's 1 million times more than the mass of our planet. The order of magnitude is 1 million times more. So going back to the galaxy, now we can do the same thing, use the same scale with the galaxy. We know that the sun goes around the center of the galaxy in 230 million years. And we know the distance of the sun to the center of our galaxy. And we compute the total mass of the galaxy from this. And now we can say that the total number of stars in the galaxy, if they were roughly the size of the sun, not all are roughly the same size of the sun. Actually, there are more stars which are slightly smaller than the sun. But the total number of stars in our galaxy sums up to 4 times 10 to the 11th power. Yeah. It's a huge number. It's 400,000 million stars if they were sort of like the sun in our galaxy. The final comment, and I will let you ask the next question is, and what about the stars in the universe? And the answer to that is, I mean, the other stars belong to other galaxies. Basically, there are no stars in between galaxies. And what we see, all the stars we see in the dark sky are stars belonging to our galaxy. That's what we see.
Yeah. So we cannot have a real estimate about the mass. That is very difficult.
We have a pretty good number on the mass. I said 4 times 10 to the 11. That 4 fluctuates slightly, plus or minus 1, actually between 4 and 6. And so the error bar, the uncertainty is very small on that, okay?
And there is here a very simple question, which is, if stars are spheres,
yep,
let's assume, why do our drawings and painting of stars have triangles and pentagons? You know, this is the popular drawing of a star. When we ask a child or someone in the street, draw us a star, they will make...
Yes, absolutely. Because those drawings come from our human part of observing the sky. And the star is some sort of poetic on one side, and on the other side, when we look at the stars, we see the stars flickering. So the way of painting and representing that flickering, since when you are drawing, you are not making a movie, you want to show someone that it's not just a dot of light. the star is flickering. So maybe that painting, that representation as a star with several points around it is a representation of that.
That is the cultural part. Maybe that depends also maybe on the civilization, on the society you are talking about. And also, we know, do they really flicker if you are outside the Earth?
Yes, of course. Yes, of course. And they flicker just because we have a strong atmosphere, which is very interesting. If you were on the moon as an astronaut and looking at the stars around you, there is no flickering. They are simple mathematical points of light, just that. So going back to the artist and the human representation of stars, let me put in some other perspective, which is those beautiful nights in which we see the stars flickering really very strongly and changing colors. An astronomer will look at that and say, my night is ruined. It's really extremely bad. I cannot, I mean, the atmosphere is bouncing the light of the stars back and forth so much, I'm losing data, I'm losing the capability of a very sharp image of the star. But for poetry, it's beautiful, and we see the change in colors, and that is our representation of stars.
And now new telescopes that point and where you connect to your mobile phone and have an image.
Yes.
It is a very colorful image that you get.
Yes.
So do stars really have those colors?
Well, there are two aspects of it. The first part of the answer is yes. The second part is they are exaggerated.
Okay.
Okay? You must take that into account. In one hand, the first part is, yes, they do have colors, but we see a very small range of colors into the stars. The amount of light they put off basically gives to the human eye just 2 or 3 different colors, no more than that.
Yeah. Besides, you have shown when talking about our exhibit that in fact those colors, how those absorption,
Yes.
emission and then absorption spectra, how they make the light that comes to our eyes.
Exactly.
And if you analyze it with a very sensitive instrument, you can see there are some colors.
Yeah.
But so you are telling me that these new tools that we have already have some image processing.
Exactly.
Okay.
The image is processed and the colors are enhanced.
Okay.
Basically, if you were in space near those nebula, beautiful nebulas that they show, I mean, we wouldn't see, the naked eye wouldn't see those colors as vivid and strong as we have in our phones or in our images. We need to make that in order, which is nice to make that because for us it enhances and allows us to see differences more easily. You see? So that is good. And if you look at the true colors one can see, basically the eye, with the cells we have to detect colors, we have the capability of detecting 3 different colors only. And looking at the temperature of the stars, we are able to see reddish stars. The very cool ones are reddish stars. Then we increase to temperatures around the sun, around 6,000 degrees, they become yellowish. And then if you increase the temperature to 10,000, the yellowish transforms into whitish stars. And if you increase the temperature, they transform into bluish stars. That's what the eye is capable of seeing about the stars. All the tonalities in between, I mean, the naked eye has some difficulty in perception, all of them. But in the pictures, yes, they are there, because the picture is enhancing that, and is enhancing that for what the cells in our brain are used, and also to make the pictures more beautiful and to be shared.
And in fact, that's why we use instruments for science and for observation. It's to expand our capabilities. We have humankind, our eyes, our ears, our senses, and like that you can have a better, well, a better sense of the universe.
Yes, of course. Let me just add another point, which is very important, which is it is necessary to have instruments and calibrated instruments because the perception of color is different from person to person. Women can see better grades of colors than men can do. But one person has a different perception from the other. So you cannot really make science because if you put your personal perception, it's going to be the way you see it. So when you use an instrument and you put filters, you put a red filter that counts the amount of light that comes into that filter. And the filter is well defined. So everybody around the world will come to the same conclusion. And then you put a blue filter. So you remove the personal touch.
The personal touch.
Of touch.
Yeah.
Yes.
So instruments not only enhance our capabilities, but they also make them more objective.
Exactly. That's the
quantifiable.
purpose.
And
Exactly.
we need that for science.
We need that. We need that for science.
So I still have here one question from these two young ladies, which is how much energy does a star have? I guess that would depend from the type of star.
Yes, of course it depends. But let me start saying this. All the energy in the star is produced at the center of the star, the core, where the temperature is really big enough, is high enough, is around 10 to the 7th, it reaches 10 to the 10th degrees. And all the reactions that produce actual energy are at the core in the star. All that energy must travel through the layers of gas that the star have. Those layers, upper layers, don't produce energy. They receive energy from the core. They are hot. If you go to the upper layer, they are slightly cooler, and as you go to the surface, the temperature goes down. But the amount of energy produced in the core is exactly the same amount of energy that comes outside at much lower temperature. So what we see from the sun is the total amount of energy that comes out of the surface of the sphere.
And
that we see the photosphere.
engine.
We don't see the engine, yes, but the engine is there. It's deadly. It kills everybody. That's gamma rays all over the place. I mean, we could not survive. But if you go to the surface where the temperature is much lower, that's what we get from the sun here on Earth. And that distribution of light, we can compute that. For the sun is about 10 to the 26th power of watts. This is joules per second. The total amount of energy that the sun puts outside per second is 10 to the 26th power of joules in all directions, in all wavelengths. If you go from all the way from the extreme ultraviolet into the infrared, that's basically where the sun, it has a peak on the green light.
So that means that we should better use it in our daily life instead of burning fossil fuels.
Let me just add something, because the answer is, the question is sort of broad.
Yeah.
And you were saying, if I go into a hotter star, the total amount increases, and decreases drastically, because with temperature it goes as temperature to the 4th power, and the price to pay is that the amount of energy released goes to these very high energy photons. Most of the energy can be in the ultraviolet, and then in the extreme ultraviolet, and then with a big tail into the X-rays.
So more energy does mean more light for the eye.
Yes,
mean,
basically that.
More X-rays and gamma rays and things like that.
Exactly.
Well, then we have, I think you have already answered this. This is João Iglesias from 10 years old. How do the stars glow?
Yeah, that's basically, I have answered that. That's basically that.
That's why you put the little pentagons.
Yeah.
Then we have an adult, Liliane Mestre, a woman with 46 years.
Old.
That when she's asking, what does the lifespan of stars depend on?
That's a very good question. And basically, the quick answer is like this. The lesser the mass of the star, the longer they live. The higher mass stars, they live very shortly. And the correct answer is they never die. If you think about, oh, when are they going to die? Okay, I will say they never die because part of the mass, the initial mass, will remain forever in the star. Remain forever.
Oh, but probably it won't glow, will it?
It will glow because when stars die, and about dying, what we are thinking is, are they shining the light that is produced in the core due to thermonuclear reactions of fusion? And the answer is, in the later stages, no, there are no nuclear reactions in the core, but they were left with very high temperatures. And that very high temperature takes too long to cool down. So the star still is there. It's not a star in the sense that the amount of light put outside comes from nuclear reactions. From that sense, it's not real a star, but is a very hot object which is giving off a lot of energy. They are hot, and they take, you multiply the age of the universe by 100, and they will be still cooling down slowly and cooling down. At that late stage, what remains from the star is not this big body anymore. It's a very small, dense core, the size of the Earth, or even smaller than the size of the Earth. Actually, the Sun is one of the cases which, at the last stage of its life, will have the size of the Earth, slightly bigger than the size of the Earth, but the amount of mass in there will be half of the mass of the Sun nowadays. So it's a very compact object. A very, if you look at the core of this, it's called a white dwarf. If you look at the core, probably there will be some nuclear reactions slowly, very slowly going on, but the whole object will be just cooling off very slowly. So how much will take? Now let me answer the question. How long does it take? And if you think about the definition of the star, that a star is an object that the amount of energy it puts off comes from nuclear reactions, the numbers vary from, let's start with the Sun as a reference. The Sun will have a life of 10 to the 11th years. 10 to the power of 11 years. We are roughly in the half of that. The Sun has lived about half of that. 10 to the 11th years is an average life for stars like the Sun. If you go to stars that are going to half the mass of the Sun, you multiply that by factors of 5 of 10 times more. If you increase the mass, for instance, if you go, let's put another number that people can think about. If you go to a star which is 10 times the mass of the Sun, the problem is the amount of mass and pressure in size produces a temperature so high that the number of reactions increases exponentially, and the star consumes this amount of mass very fast. And the star of that is only 10 million years. And it blows up in the end.
Oh, we are happy that the Sun is not like that.
Exactly.
We are really happy.
Exactly, yeah. If you are start searching for planets with life, you don't search for planets in life in stars like that, because they don't last for billions of years.
Yeah.
It's just millions, tens of millions, which is not.
So it's just an instant in the
It's an
universe.
instant, yeah.
So there is less probability of finding life there because maybe it had no time to evolve or something.
That's exactly that. Yeah. I mean, these stars can have planets. The problem is the planet doesn't have a lifespan long enough to develop intelligent life, because when the chemistry is building up some complex molecules, the star in itself blows up and destroys basically all the chemistry on top of, on the surface of the planet, and afterwards the planet simply will cool off. And with no chances to build. With no chances,
yeah. And on the other way, with those remnants of those supernova, you produce heavier elements that are needed for other creatures like us to be built.
Well, it is. If you look at the history of the Sun and our place in the galaxy, And if you look at the chemical composition we have in our sun and the stars around us, you come to the conclusion that in this area, we are inside sort of a bubble inside the galaxy, where previously to the sun, probably we have traces about 24, 25 supernova happening before the birth of the sun. And what they have produced was this, I would say, higher abundance of heavy elements, chemical elements. But even when I say higher, it's only 2% of the total stuff.
In any case, that suits us well because we are done of it.
Yes,
we are
of
part
course.
of it. We are part of the universe, and we are made of exactly the same elements as you showed in your video presentation.
That's exactly.
I think we are arriving to the end. There was here another question by Rodrigo Mestre, what happens to a star when it dies, but you have answered.
Basically, I have given some answers to that as well.
And we are also part of the results of the remnants.
Yes, we are.
And so I think that there are no questions coming from...
There is one question.
There is one question?
Yep.
No, there is, okay. There are no more questions, so maybe we can just go back to what you have shown. You have shown that our exhibit here about the spectra of gases can be used to explain astronomy, to explain what are stars made of and why we know that all matter in the universe is built of the same building blocks, which are the elements of the periodic table, which, by the way, last year we commemorated 100 years of Mendeleev organizing all the elements of the chemical elements in a very practical table, really practical to take to school, to be with you in any place, to know what the elements exist. And now he answered